MS Ramaya University of Applied Sciences.
Hi students, let us discuss about Kaplan turbine. We have seen the flamboyant chakra firecracker during Diwali. It rotates with such high speed on firing. Also a rotating garden sprinkler that is used to water the lawns in a garden. The energy for the rotation is brought about by the reaction force from the exciting fluid. This forms the basic principle for a reaction turbine. Pelton wheel is an impulse turbine where the impulse due to the kinetic energy of the fluid is responsible to convert it into rotations of the shaft. In a reaction turbine, it is the reaction force acting on the turbine blade which is made use to rotate the turbine shaft. The reaction force arises from the fluid gliding over the turbine blades. The main advantage of reaction turbine is that it can be used wherever the high head of the fluid is not available. Kaplan and Francis turbines are very good examples of a reaction turbine. In the current experiment, performance analysis of a Francis and Kaplan turbine test rig is carried out. Kaplan turbine is an axial flow low head turbine. In this turbine, water enters and exits the turbine in axial direction. These turbines are used when available head of water is 2 to 40 meter. Its construction is similar to an air propeller. Linganamakki, Kadra, Alamatti dams are few examples in Karnataka where Kaplan turbines are installed. Kaplan turbine consists of a casing and guide vane or a wicket gate. In the casing, water enters the turbine through guide vane at uniform velocity throughout the circumference. Further, water enters and exits the turbine runners in axial direction. The runners experiences reaction force due to the fluid gliding over the blade with some pressure drop. Turbine shaft is connected to an alternator where the mechanical energy from the turbine shaft rotations is converted to electrical energy in a generator. At the exit of the turbine, pressure is negative. Hence, a draft tube is provided for pressure increase up to atmospheric condition. It avoids reverse flow of water and cavitation. In the figure, the volute casing and the guide vanes of a Kaplan turbine are seen. Also, the turbine blade can be observed. The blade angle of a Kaplan turbine can be adjusted. In case of a high power demand, high discharge of water is allowed for which blades can be adjusted in an axial direction. For a lower discharge of water, the blades can be adjusted in a tangential direction. The opening and closing of the guide vanes helps in controlling the flow rate of water to the turbine. Francis turbine is a mixed flow medium head turbine. In this turbine, water enters in radial direction and exits in axial direction. These turbines are used when available head of water is 45 to 400 meters. The pressure head goes on decreasing as the water flows over the runner blades. The static pressure at the runner exit may be less than the atmospheric pressure. The change in pressure while water is gliding over the blades is called reaction pressure and is partly responsible for the rotation of the runner. A typical Francis turbine blade can be seen in the figure. The turbine blade is designed in such a way that the initial part of the blade experiences reaction force, whereas the latter part experiences impulse. Hence, the turbine shaft starts rotating due to the combined effect of the reaction force and the impulse. The Francis turbine consists of a volute casing that allows uniform velocity of the fluid to enter the turbine in a radial direction throughout the circumference. Inside the casing, stationary and guide vanes are installed to guide the water from the casing into the runner in a radial direction. Guide vanes can be operated to open or close for controlling the flow rate of water and also varying the angle of attack to the runner. After passing through the guide vanes, water enters the runner in radial direction and exits the runner in axial direction. The runner experiences force of reaction and also impulse. Turbine shaft is connected to an alternator where the mechanical energy from the turbine shaft rotations is converted to electrical energy in a generator. At the exit of the turbine, pressure is negative. Hence, a draft tube is provided for pressure increase up to atmospheric condition. It avoids reverse flow of water and cavitation. The picture shows a Francis turbine with its casing, guide vanes and runner. Cavitation occurs especially at spots where the pressure is low. Due to cavitation, the efficiency of a reaction turbine decreases and causes crackling noises. The main problem is the wear or damage of the turbine's parts such as the blades. At the turbine exit, pressure is below atmosphere, hence a draft tube is installed at the exit to raise the fluid pressure up to atmospheric. At MSR UAS laboratory, a combined Francis and Kaplan turbine test rig is installed to analyze the performance of each turbine. The discharge of the water coming into the turbine is calculated using the differential pressure in the venturi meter. Using the discharge and head of the water, hydraulic power input is calculated. Incandescent bulbs are illuminated, thereby loading the turbine, whose value is directly obtained on the watt meter. Efficiency of the turbine is calculated as a ratio of output power to the hydraulic power. Specific speed of the turbines are also calculated and plots of discharge against head, discharge against efficiencies, load against efficiencies and specific speed is plotted.
Hello everyone. Today we will be conducting an experiment to analyze the performance of Francis and Kaplan turbine test rig. This experiment consists of both the Francis and the Kaplan turbines. The experimental setup consists of a storage tank which is used to store the water. From the storage tank, it is connected to a centrifugal pump which pumps the water to the turbines. Here we have a deviation. Either we can divert it to the Kaplan turbine side or we can divert it to the Francis turbine side. Now we shall divert the water from the centrifugal pump towards the Kaplan turbine side by opening the Kaplan turbine butterfly valve. Once this is opened, we will know that the water is flowing in this side of the pipeline. Further, we have a venturi meter on the pipeline which will give the discharge of the water flowing through the pipeline. we have a solenoid valve at the inlet as well as at the throat. Using these valves, we can actually make the water to flow through the pipes, from where we can measure the pressure at the inlet as well as at the throat of the venturimeter. Further, the water with high pressure enters the Kaplan turbine over here. Further, from the guide vanes, the water enters the turbine axially. Now, this is the turbine. The water enters the turbine in the axial direction and also exits in the same axial direction. This is the Kaplan turbine blades. Now, this blade is in the most axial position. We can also rotate the valve and then vary the angle of the blade. We can make it either in the tangential or the axial position. From the exit of the turbine, it is connected to a draft tube. We know that at the exit of the turbine, we have a pressure which is below atmospheric, and by making use of the draft tube, we can increase the pressure of the water and then bring it to the atmospheric pressure. The shaft of the turbine is connected to an alternator using a V-belt drive. The alternator converts the mechanical power that the turbine generates into electrical power. Here we have 10 incandescent bulbs of around 150 watts each, which can be switched on, and thus the turbine can be loaded up. On the panel, we can see a toggle switch between manual and computerized. Since we are conducting the experiment manually, we have to keep the toggle switch towards the manual. And these two switches are for the solenoid valves on the venturimeter. We can switch on those switches which are with reference to that particular turbine. Since we are conducting the experiment on the Kaplan turbine, we shall switch on the Kaplan solenoid. We also have a pressure measurement for the venturimeter. Here we get the reading for the venturi inlet pressure, and here we get the reading for the venturi throat pressure. Both these pressures are in terms of kg per centimeter square. Here we get the speed of the alternator, which is measured using the proximity sensor. The measurement, which is indicated over here, is in terms of revolutions per minute. The turbine outlet pressure can be measured over here. The indication is in terms of kg per centimeter square. The measurement is taken place just before the draft tube after the turbine exit. As we know, there are incandescent bulbs which are connected to the alternator. We can switch on the 10 incandescent bulbs over here. Once the few bulbs are switched on, the relevant power that the bulbs are extracting can be indicated over a watt meter here. Here the readings will be in terms of watts. This is nothing but the power output from the turbine. Now let us go ahead and conduct the experiment. Before starting the experiment, we have to switch on the MCB switch. And since we are diverting the water towards the Kaplan turbine side, we have to keep this butterfly valve in fully open condition. Once we have set the Kaplan turbine blades in a particular direction, we can switch on the motor for the centrifugal pump to pump the water into the turbine. We can observe that the turbine has started rotating, and now we shall load up the turbine by switching on few bulbs. Here we can observe the inlet pressure and the throat pressure of the venturi meter. The speed of the alternator can be observed over here. The turbine outlet pressure, which is lower than the atmospheric pressure, can be observed over here. And also the power extracted by the incandescent bulbs is indicated on the watt meter over here. Now the same experiment can be conducted for different loading pattern, that is switching on another few bulbs. Now I have switched on all the 10 bulbs, so this is 100% load. The same readings can be taken at this loading as well. We must note that for all the different types of loading, it should be at a constant head. The constant head of around 1 kg per centimeter square should be maintained throughout the experiment. Once all the readings are taken, now we can switch off the pump. We have conducted the experiment on Kaplan turbine at constant head. Now the same experiment can be repeated at constant speed. Now the constant speed for the alternator can be controlled by operating the butterfly valve. Now we have conducted the experiment on both constant head as well as constant speed. We take down the inlet pressure and throat pressure of the venturi meter, using which we can calculate the discharge of the water entering the turbine. Hence, we can actually calculate the input power, that is the fluid power entering the turbine. We also can measure the output power from the incandescent bulbs extracting from the alternator, and hence we can calculate the efficiency of the turbine. Also, we can plot discharge against head, discharge against efficiency for the same turbine. And that concludes the experiment. We have conducted the experiment on a manual basis. The same experiment can be repeated using a computer, which can be connected over here using RS485 converter. The loading of the incandescent bulbs and also switching over from Francis to Kaplan turbine for the venturi meter solenoids can be controlled using LabVIEW software on a computer. And the same experiment can be repeated.
The experiment on Francis and Kaplan turbines by operating it manually. Now we shall repeat the same procedure using a computer. For that, we shall open the Francis and Kaplan application. Right click on the application and select Run as Administrator. Now the application is open. The first thing that we need to do is select the COM port. On the drop down button, select Refresh. LabVIEW automatically detects the COM port. In this case, it is COM1. Select the COM port and click OK. We can select the type of the turbine, either Francis or Kaplan. Here we shall select the Francis turbine. Also, we can select the type of the blade or the guide opening, 1/4, half, 3/4 or full wall opening. I shall select the half blade opening. Next, we need to start the test. So on the left side on the panel, click Start Test, and we need to select a file name inside which all the data can be logged. Type the file name and then select OK. Once this procedure is completed, we can observe some values that has appeared on the screen. These are the same values which is on the main panel. Once this procedure is completed, we can observe some values that are appearing on the screen. These are the same values that are displayed on the main control panel of the experimental test rig. Now the main pump is switched on from the control panel, which shall provide the fluid to the turbine. We can observe the different values appearing on the screen. Also, at the bottom of the screen, we can observe some of the instantaneous parameters like discharge, head of the turbine, input power, and the shaft power. Here we can observe that the shaft power is showing 0 because there is no load on the turbine. To load up the turbine, we can switch on the bulbs which are connected to the alternator to the turbine over here. Now we can observe some shaft power appearing on the screen. At this loading, we shall log the data. We can see all the data has been logged and is being displayed on the screen. The same data is being stored in the Excel file that has been shown before. For another set of readings, another 3 bulbs are switched on and the data is logged again. We can observe that the speed has reduced. We shall take the final set of readings by switching on all the bulbs connecting to the alternator of the turbine, and the data is logged again. We can observe that the inlet pressure to the turbine is constant, and also the different performance of the turbine can be observed in these three tabs, where different plots regarding the performance of the turbine is automatically plotted by the LabVIEW software. These plots are plotted as and when the data are being logged. Now we shall conduct the same experiment at a different guide vane opening. For that, let us switch off all the bulbs and manually set the guide vane opening to 3/4 or 75%. Once the valve is set to 75%, on the computer select 3/4 guide opening. Now the experimental procedure is repeated again by switching on 3 bulbs and loading the turbine. The data is being logged. The same procedure is repeated for another 3 bulbs and the data is logged. We can observe that the inlet pressure to the turbine is almost a constant around 1 kg per centimeter square. In this manner, we can conduct the experiment on the turbine for different guide vane openings and also at different loads. Once all the readings are being taken, all the bulbs are switched off from the computer. And the pump is stopped on the main control panel. Now we shall stop the test, and that concludes the computerized operation of the turbine. The same experiment can be repeated for the Kaplan turbine as well. The log data can be observed on the Excel file, which is saved at the destination folder. All the values are also appearing on the Excel sheet. So these values can be used to do further performance analysis manually. The experiment then can be repeated for the Kaplan turbine. So this concludes the experiment on the computerized Francis and Kaplan turbine test rig.
To conduct the experiment for the Francis turbine, we have to close the butterfly valve for the Kaplan turbine and open the butterfly valve on the Francis turbine, such that the water from the centrifugal pump is being diverted towards the Francis turbine side. Once the butterfly valve on the Francis turbine line is opened, the water flows in this pipeline, which is connected to a venturi meter. This pipe will give the pressure at the inlet of the venturi meter, and this pipe over here will give the throat pressure of the venturi meter. Using these two pressures, we can calculate what is the discharge of the water flowing through this pipeline. Further, at the downstream of the venturi meter, the water flows into the Francis turbine and enters radially. The water enters the Francis turbine radially in all the directions, and once it enters, we can see there are guide vanes present at the entry of the turbine. These guide vanes can be either opened completely or closed. Thereby, we can control the discharge of the water that is entering the turbine and also change the angle of attack of the turbine. The guide vanes angles can be changed by rotating the valve which is present behind the turbine. The shaft of the Francis turbine is connected to an alternator via a V-belt drive. The water enters the turbine radially and exits axially. In this exit, we have a draft tube. We know that at the turbine exit, the pressure is below atmosphere, and hence the draft tube will be used to increase the pressure and get the pressure of the water to atmospheric condition. The experimental procedure for Francis turbine remains the same as that of the Kaplan turbine, but we have to make sure that the solenoid switch for the Francis turbine is kept on. This will ensure that the pressure from the venturi meter is coming from the line connected to the Francis turbine. Even for the Francis turbine, we shall switch on few number of bulbs and load up the turbine, and hence calculate the inlet pressure, throat pressure of the venturi meter and the turbine outlet pressure, along with alternator speed and the power from the incandescent bulb that is being extracted from the alternator. Hence, the efficiency of the turbine and also the plots of discharge against head and discharge against efficiency can be plotted. Here, we can also conduct the experiment at constant speed by operating the butterfly valve before the venturi meter, and hence we can calculate the efficiency at constant speed as well. And that concludes the experiment for Kaplan and Francis turbine test rig.
At MSR UAS, we spark your imagination unlike any other.